So many people have heard about how to sum a finite sequence or sum even an infinite sequence. But how do you actually sum a sequence or a set of numbers that is not even countable? It's not ordered. So this video is based on the Stack Exchange post about the sum of an uncountable set of positive numbers. So the question in this Stack Exchange post is a little bit different from what I'm going to talk about. And basically what this says is that if you have a collection of real numbers that are positive, right? And such that the sum of all the numbers in that set is, with a set of collection or collection, it's the same thing, is less than infinity, so it's finite, then at most countably many numbers cannot be zero. So basically, if you rephrase this, you can say that the sum of an uncountable set is infinity. So the idea of this proof is that we want to bound A by the bottom by some number. It doesn't matter how small. We just have to bound it by something and make sure that it doesn't go to zero too quickly, right? So first, we're going to let all elements be positive, or else you can't really sum if all elements are not positive. So which means that which means you could sum in different orders and get different sums, which just doesn't make sense. So for every n in natural number, we're going to let an be a subset of A such that the subset is greater than 1 over n. So we're kind of like naming different copies of A with different conditions such that, the union becomes A. Since we know that A is uncountable, that means that all the subsets cannot be also countable, because the countable union of countable subsets is countable. So that means that either A1 or A2 or any A, one of these must be uncountable. And when one of these are uncountable, that means that you can pull as many elements as you need for it to be greater than any m that you choose, which is the definition of infinity, right? Remind that the definition of infinity, or how you can show that a series is infinite or have something sum to infinity, is if for every m that's very large, you can choose enough elements from A to sum to be greater than that. Now let's just assume A3 is a set that was uncountable. So that means that since A4, A5, every natural number greater than 3 would also have an uncountable cardinality, which means that an, which is A3 union A1 and A2 that have elements that aren't in A3, would sum to greater than A3, which means that if A3 is infinite, that means that an must also be infinite.